Okay, I think it was based on chapters 1 and 2. So this test, I'm going to let it will be covering chapters 3, 4, and 5. Now, I need to get back to you your graded chapters 4 and 5 assignments so that you can have that to review. So I'll see if I can, well, I should be able to get that back to you by Thursday. And the test will be the Thursday of next week, all right? So that test will cover chapters 3, 4, and 5. And, oh, you had a question? You won't be here this Thursday or next? Unless you can come by my office during my office hours, or I could make an arrangement for you to do it in the testing center. So we can talk about that later. Okay, so that's basically it as far as that test is concerned. And so what I'm going to do now is proceed with chapter 6. So you won't be tested on chapter 6, which is what we're in the middle of right now. Okay, so let me, oh, I need to get rid of this thing here. All right, so chapter 6, thermochemistry. Let me see here. Get my screen. Okay, so if I recall, the last thing we discussed was this right here, these two examples. So the next topic will be how do we solve certain problems involving both enthalpy changes and stereochemistry, all right? And the key thing you need to remember, well, a couple of things actually you need to remember when it comes to solving these problems. First of all, we can consider for exothermic reactions, heat is produced, so we can be treating heat as a product, just as though we treat, you know, chemical substances formed in a reaction as products. And then, of course, when heat is absorbed in an endothermic reaction, we can treat heat as a reactant, all right? And, excuse me, based on that, we can basically come up with conversion factors involving delta A. So for example, let's look at this reaction. The reaction between hydrogen and chlorine to form HCl. The equation is balanced and you're given the enthalpy change for that reaction. So we can actually write down some conversion factors which involve this magnitude of delta H, such as these three right here. So for example, for every 1 mole of hydrogen reacting, this is the amount of heat change occurring. So we can represent it as this conversion factor. And then we can do something similar in the case of chlorine, and we can do something similar in the case of hydrogen chloride. So just as how you can use conversion factors to represent relationships between different substances, you can also include enthalpy as a part of that as well. Again, depending on the type of question you're dealing with. And I think the next slide is an example of such a question. In fact, it's using the same equation here. And the question is asking here, what is the enthalpy change associated with the formation of 5.67 moles of HCl gas in this reaction? And it gives you the equation, it gives you the enthalpy change. So the first thing I would do here, I'm going to do the problem up here. I'll write down what is given in terms of the moles of HCl. And then I will multiply this by the appropriate conversion factor, which would have 2 moles of HCl down here. So I should have HCl here. And up here, I'm going to put this value right here, which is minus 184.6 kilojoules. And then you do the number crunching times 184.6 divided by 2. So according to my calculation, the answer is minus, how many sig figs? 3 sig figs, so minus 523 kilojoules. So that would be the answer. All right, so that's a relatively simple problem. We're combining what we just learned with respect to enthalpy, changes, and stoichiometry, basically. All right. Okay, any questions about this? Any questions? Any questions? All right, continuing. So let's talk about calorimetry, which is basically dealing with the measurement of heat flow, right? And heat flow can occur in a physical change as well as a chemical change. And the instrument that we use to measure this heat flow is known as a calorimeter, all right? And there are several levels of sophistication in terms of designs of calorimeter. So what you see here on the screen is the ultimate in low tech when it comes to this sort of measurement, right? We call this a coffee cup calorimeter. And basically it's made up of 2 styrofoam cups. Styrofoam, of course, is the material of choice because styrofoam, as you may or may not know, is insulating. So therefore, any reaction or any changes taking place inside, as long as it's a closed system, you won't have any exchange of heat or energy between what's inside and what's outside. So that's why we use the calorimeter. In addition to the 2 cups, we have this stopper here, which has 2 holes. One hole, you're going to push a thermometer through. The purpose of the thermometer is to measure any temperature changes occurring. Okay, why did this happen? Okay, and then here we have a stirrer pushed through the other hole. Purpose of that is just to make sure that everything is homogeneous in terms of the reaction taking place inside the 2 cups. And then we have a more sophisticated instrument here. It's called a bomb calorimeter. And this is used in particular when it comes to measuring heat flow, when it comes to organic reactions, or I should say organic compounds undergoing combustion reactions, right? And it's definitely more sophisticated than what we have here in the case of the ordinary coffee cup calorimeter. You have what we call a steel bomb, which is basically a very, how should I put this? It's basically like a container, but it's very, it can withstand a lot of hits and all of that. Inside it, you have the substance that is undergoing the combustion. You have 2 electrical wires, which is connected to an electricity source. And what that does is that it ignites the substance inside here. Heat is generated. The heat is basically passing through the walls of this container, goes into the water. Temperature of the water increases. You can measure the increase in temperature. And based on that, you can determine the amount of heat change occurring as this reaction is taking place, all right? So these are just 2, different instruments used to measure these sort of changes in energy. Okay, so some terms we need to talk about, and some of these you should have met before in your introductory chemistry or high school chemistry. So basically when we're using these instruments, calorimeters, you have to be careful in terms of considering the relationship between the heat change occurring inside the calorimeter and the heat change of the calorimeter itself. So as stated here, the heat evolved in a reaction is absorbed by the calorimeter and its contents, right? So basically, if the reaction is producing heat, then that heat will be absorbed by the calorimeter, right? So of course, we can monitor the energy change by looking at the temperature change, right? To determine whether or not heat is produced or absorbed in a reaction. So at this juncture, I want to introduce to you a couple of terms. The first of which is what is known as the heat capacity, right? The definition is given right here. It is the amount of heat required to change the temperature of the system by 1 degree Celsius or alternatively 1 Kelvin. It doesn't matter if the temperature is measured in Kelvin or Celsius. Basically, that's the definition. And the formula for calculating the heat capacity is given right here. It's uppercase C is equal to Q divided by delta T. Q is the heat change and delta T would be the temperature change, all right? So therefore, as a result, the units of heat capacity is joules per degree Celsius, or it can also be expressed as, write it down here, joules per Kelvin.
It's gonna be a challenge for us, but you know, if we can control, we control.
All right. So that's basically what the heat capacity.
That's all like 70 on the team and everybody just.
Okay, I'm hearing some. For you guys out there in Zoom, could you mute yourselves, please? Okay. Now, here's another term here. Now, to be perfectly honest, I don't expect us to be working with this a lot, but I'll just give it to you anyway. Molar heat capacity, it is the heat capacity of 1 mole of a substance. And then this one, specific heat, we definitely will be working with this, and you should have met this before. In fact, the specific heat of a substance is the heat capacity of 1 gram of the pure substance. All right, so basically, the heat capacity, or I should say the specific heat, which is expressed as lowercase c, will be equal to uppercase C, which is the heat capacity divided by the mass of the substance, right? Now, because we know that C is the same thing as Q over delta T, then when we plug that into this equation, this is what we end up with. The specific heat is equal to Q divided by M times delta T. Or you can express it this way. Q is equal to C times M times delta T, right? The heat change for a substance is equal to the specific heat times the mass times the change in temperature. All right, so based on what we have just learned, we should be able to do this question. The question says, calculate the heat capacity of aluminum that must absorb 629 joules of heat from its surroundings in order for its temperature to rise from 22 degrees Celsius to 145 degrees Celsius. So the equation we're going to use here is Q is equal to M times C times delta T, all right? But the question is asking for C. So we can rearrange this to get C is equal to Q divided by M times delta T. So all we have to do from here is plug the numbers in. Q is equal to 629 joules. M is the mass. Oh, shoot. I'm sorry, wrong equation. I should be using the equation for heat capacity, not specific heat. So let me erase all of this here and restart. Okay, so the equation that should be used should be uppercase C is equal to Q divided by delta T, right? So Q is 629 joules. And I should add that because it says it's absorbing this much heat, that means Q will be positive, and you're going to divide by delta T. Delta T is a change in temperature. Change in anything is always the final value minus the initial value. So in this case here, we're going to put 145 degrees Celsius minus 22 degrees Celsius. And then we do the calculation. So let me do the bottom part first. 145 minus 22, that gives you 123, and then divide 629 by that. And according to my calculations, this works out to be equal to 5.11, and the units here would be joules over degrees Celsius. And that would be the answer. All right, so that's a relatively simple problem, which I was actually making more complicated than it should be. Okay, any questions about this? Any questions? Any questions? All right, moving along. So let's talk about specific heat. So this is the equation here, which I talked about earlier. In some textbooks, they use the symbols M for mass, C for specific heat, and delta T is still delta T, right? So that's basically the equation for calculating the heat change based on the specific heat, the mass, and the temperature, right? So when you're using this equation, you have to be careful about the sign that's associated with some of the terms, especially when it comes to heat and the change in temperature, right? So as stated here, if delta T is positive, right? If delta T is positive, that means that Q is positive, right? Because the mass and specific heat is always positive, right? So if delta T is positive, that means Q is positive. So what does that mean? That means that the system is absorbing heat, which makes sense. If the system is absorbing heat, then the temperature of that system will increase, right? And then, of course, the reverse is true. If delta T is negative, that means that Q is negative, which means that the system will be losing heat. All right. So, you know, a lot of this is common sense, you know, based on experience and so on. Now, there's another unit of energy known as a calorie unit. It's not an SI unit, but it is still used, especially by engineers. And the relationship between the calorie unit and the joule unit is given right here. 4.18 joules is equal to 1 calorie. All right, so based on that unit, the specific heat of water will be 1 calorie per gram degree Celsius. In fact, the calorie unit is actually based on the properties of water in this regard. And then there's another unit of energy. This is typically used by nutritionists. It's called the food calorie, which is the unit is expressed as uppercase CAL or kilocalorie, and it's actually equal to 1,000 of the calories that we just talked about here. All right, so that's another unit of energy that is used in the case of the field of nutrition. Okay, and here we have a list of substances and their different specific heats. So specific heats is basically a physical constant, you know, kind of like melting point, boiling points, densities, and so on, right? And what you'll find is that metals typically have relatively low specific heats, right? Water has a very high specific heat compared to everything else, and that has to do with a particular phenomenon known as hydrogen bonding, all right? And we're going to talk more about hydrogen bonding later on in this course, all right? So this is just, you know, a very small table giving you some specific heats of different substances. Okay, so let's look at these examples here. It says here, how much heat in joules and in kilojoules does it take to raise the temperature of 225 grams of water from 25 degrees Celsius to 100 degrees Celsius? So let me get out of this here, and let me open up. What should I open? Let me do the word, use Word. Okay, and then let me go back to this. Let me copy this question and paste it here in Word. And then make this a bit larger. And where is the writing thingy? Okay. So the question says, how much heat in joules and kilojoules does it take to raise the temperature of 225 grams of water from 25 degrees Celsius to 100 degrees Celsius? So the equation you'll be using in this particular case is Q is equal to M times C times delta T. So they gave you the mass. Now C would have to be given, as I said before, it is 4.18 joules per gram degree Celsius. And then delta T would be the change in temperature. It's the final temperature minus the initial temperature. So it's going to be 100.0 degrees Celsius minus 25.0 degrees Celsius. All right. And basically you have to do the computation after this. Now this part here within the parentheses, I would work out first. And that would be equal to 75.0 degrees Celsius. And then I would do the rest. So that's 225 times 4.18 times 75. And according to my calculations, when this is rounded off to 3 sig figs, according to my calculations, this works out to be equal to 7.05 times 10 to the 4 joules. All right. And that answers this part of the question, because the question also asks for the answer in kilojoules. So to convert that to kilojoules, you'd multiply by 1 kilojoule above, 1,000 joules below, and the joule units will cancel out. So basically you divide by 1,000. And according to my calculation, this works out to be equal to 70.5 kilojoules. And that's it. All right. Okay, any questions about this? Any questions? All right. So let me go back to the PowerPoint here. The next question says, what will be the final temperature if a 5.00 gram silver ring at 37 degrees gives off 25.0 joules of heat to its surroundings? And it says use the specific heat of silver listed in table 6.1. So that means you have to use the specific heat provided here for silver, which is 0.235 joules per gram degree Celsius. So let me, okay, what am I going to do here? Let me copy this here. And then let me paste it onto the Word document here. And let me get rid of all this here. Okay, so now when you're doing this question, you have to be careful. You have to pay attention to how the question is worded, because the way the question is worded will give some indication as to the signs for some different terms. All right. It says, what will be the final temperature? Right. So I'm just going to use TF here to represent the final temperature. That's what the question is asking for. It gives you the mass of the ring. It gives you the initial temperature. It says that it gives off 25.0 joules of heat. So what does that tell you about the heat in terms of the sign? If it gives off, it means what? It's going to be negative, right? Okay, so those are the things you have to pay attention to. And the specific heat for the ring is 0.235 joules per gram degree Celsius. So this is the equation we're going to use. Q is equal to M times C times delta T, right? So since the question is asking for the final temperature, what I will try to do is find out what the change in temperature is. So the change in temperature will be equal to Q divided by M times C. So we put the numbers in. Q is going to be equal to minus 25.0 joules over M, which is 5.00 grams times C, which is 0.235 joules over gram degrees Celsius. And please, I don't know if I'm quite sure I've said this before, but I'll say it again. When you're setting up your equations, make sure you include your units as a part of the whole setup, because as you're going to see here, you can see how the units will cancel out. So the only unit remaining here for the change in temperature is degrees Celsius. So let me do the calculation here. It's minus 25 divided by 5 divided by 0.235. Okay, so according to my calculations, this works out to be equal to minus 21.3 degrees Celsius. Let me do this again just to make sure. It's minus 25 divided by 5 divided by 0.235. Okay. Okay, so that's a change in temperature, right? Now, let me do it up here. The change in temperature is going to be the final temperature minus the initial temperature, right? What the question is asking for is the final temperature. The question gave you the initial temperature and you just calculated delta T, right? So basically, the final temperature is going to be equal to delta T plus the initial temperature. Now, delta T is minus 21.3 degrees Celsius, and the initial temperature is 37.0 degrees Celsius. So when we work that out, 37.0 minus 21.3, you're going to get 15.7 degrees Celsius. And that would be the final answer that is being asked, right? And of course, it makes sense. The final temperature is going to be lower because the ring is losing heat, all right? Okay, any questions about this example? Any questions? Any questions? Okay, let's go back to the PowerPoint. All right, so here's another example. Now, this one involves not only specific heat or the equation for specific heat, but it also involves the law of conservation of energy. So let's look at what the question says. The question says that a 15.5 gram sample of a metal alloy is heated to 98.9 degrees Celsius and then dropped into 25.0 grams of water in a calorimeter. The temperature of the water rises from 22.5 to 25.7 degrees Celsius. So the question is asking for you to calculate the specific heat of the alloy. Okay, so think about what's happening here. You're starting off with a metal sample, which is relatively hot, 98.9 degrees, right? And you're going to add it to water, which has a temperature initially of 22.5 degrees Celsius, right? So what's going to happen is that when the metal comes into contact with the water, there'll be a heat transfer, right? The heat will be transferred from the metal to the water, right? So what's going to happen to the temperature of the metal? The temperature of the metal is going to fall while the temperature of the water is going to rise until we get to a state of thermal equilibrium, where the temperature of the metal and the temperature of the water will be the same. So basically, this final temperature here will be the final temperature of both the metal and the water, right? So how do we solve this? Well, firstly, we're going to write down the relationship between the heat change for the metal and the heat change for the water. Remember, the metal is losing heat while the water is absorbing heat. So what does that mean? That means that the heat change for the metal is equal to minus the heat change of the water, right? Because the metal is losing heat and the water is gaining heat. The amount of heat gained by the water is the amount of heat that is lost by the metal. I hate this color. Let me change this to black. Okay. So what I'm going to do now is write down separate expressions for both Qm and Qw. Now remember, Q is equal to M times C times delta T. So this expression here, I'm going to write down specifically for the metal on this side of the equation and for the water on the other side of the equation. So for the metal, I'm going to write down that the mass of the metal times the specific heat of the metal times the change in temperature of the metal would be equal to minus the mass of the water times the specific heat of the water times the change in temperature of the water, right? Now, remember, the question is asking for this right here, the specific heat of the metal. So we have to isolate it on one side of the equation. How do we do that? We divide both sides by what? What do we divide both sides by? Anybody? If we want to isolate the specific heat of the metal, Cm, on the left side, what do we divide both sides by? The mass of the metal and the change in temperature of the metal, right? Because that will cancel with that will cancel with that, and we have to divide this side by the same thing. Mass of the metal times the change in temperature of the metal, right? So basically, all we have to do from here is to plug in the different values into this equation based on information provided in the question. So here now we have to be careful. We have to make sure that we put the right numbers in the right places on the right side of this equation. So the first thing we're going to input on the left side, on the right side, I'm sorry, is the mass of the water. What's the mass of the water? 25 grams, right? So we're going to put 25.0 grams here, multiplied by the specific heat of water, which would have to be provided to you, 4.18 joules per gram degree Celsius. And then we multiply by the change in temperature of the metal, right? What's the change in temperature of the metal? It's the final temperature of the metal minus the initial temperature, right? Remember I said that the final temperature of the water would be the same thing as the final temperature of the metal, right? So here we're going to put 25.7 degrees Celsius minus the initial temperature of the metal, which is 98.9 degrees Celsius, all right? And then now we divide all of this by the mass of the metal. What's the mass of the metal? 15.5 grams times the change in temperature of the metal. What's the change in temperature of the metal? Final temperature, which is 25.7, minus, oh, wait a minute. I made a mistake. Okay. I just realized something. Right here is where I made a mistake here, because this should be the change in temperature of the water. I'm sorry about that, folks. So let me take out my eraser here and erase this here. The change in temperature of the water is the final temperature minus the initial temperature of the water. So this here, I should have written 22.5. So here should be 22.5. I apologize for that, folks. All right. Here is where we're going to have the change in temperature of the metal. The final temperature, which is 25.7 degrees, minus the initial temperature, which is 98.9 degrees. All right. So this underscores the importance of making sure that you place the correct numbers in the correct places. All right. I just made an error that could possibly lead to, well, that would definitely lead to the wrong answer. It's a good thing I caught it. Okay. So basically all you have to do is, you know, put the numbers in the calculator. Now, what you'd have to do, of course, is work out what's in the parentheses first. So within this parentheses, you have 25.7 minus 22.5. And according to my calculation, that's 3.2 degrees Celsius. And then for below, 25.7 minus 98.9. And according to my calculation, this part gives minus 73.2 degrees Celsius. And then you do the rest. So let me do that right now. 25 times 4.18 times 3.2, and then divide that by 15.5 divided by minus 73.2. And because of this minus sign here, the final answer would be positive. And according to my calculation, it works out to be 0.21. And in terms of the units, the grams will cancel out here and here. Degrees Celsius will cancel out here and here. So the only unit remaining would be joules per gram degree Celsius. And that's it. And that's how you do that. All right. Any questions about this? Any questions? Joules per gram degree Celsius. Joules / grams degree Celsius. All right. Any other questions about this example? Any other questions? All right. So based on what we just covered, now, if I remember correctly, we stopped at question number 2, right? For assignment number 6. So you should be able now to do questions 3, 4, 5, and 6. So I want you to get on. Did I give you these already, right? You all have copies? Oh, you don't? Anybody else needs a copy of this? So you can get started on questions 3, 4, 5, and 6. And of course, if you have any questions, feel free to ask. Okay, let's see here. Yes, ma'am. Hold on, let me check here. Yeah, I do have a score for you here. I guess I wasn't completely sober when I was submitting the grades in Canvas. Okay, so let me go here. Check this out. Miss Elwell, right? Okay, I got you. I got you, I got you. It's there now. Mhm.
Yes, I share all my secrets. Like it, I have a question. Okay, came across my desk, like, talking about. Yeah, sure, what is? My why you didn't like it for the Caroline look so much. But you're asking a lot of an old man's memory. If he had an alibi, for starters, he did. What the problem? Leave it alone.
Oh, okay. Wait, you check them. I don't remember. You got that. Oh, check you right there. Right here. Anyway, I got the bag over there. I got all the cancel and all cancel and eat right. That's I got the bag over there.
Okay, so where we. Hold on, get my copy. Where are we at with assignment 6? Have you all done up to question 6? Going once? Going twice? Have you all done question 6? No? I'm sorry? All right, well, tell you what, let me, for the rest of the time that we have here, let me just continue with this here. Okay, we covered that. All right, let me see here. All right, let's look at this example here. It says a 50 ml sample of a 0.250 m hydrochloric acid and 19.50 m, I'm sorry, degrees Celsius is added to 50.0 mils of a 0.250 m sodium hydroxide, also at 19.50. I guess I need to share my screen, huh? How could I forget? Okay, so basically you're mixing sodium hydroxide, 50 mils, 0.250 m at 19.50 degrees Celsius to hydrochloric acid, same molarity, same temperature in a calorimeter. And it says the solution temperature rises to 21.21 degrees Celsius. So the question says here to calculate the heat of this reaction. Okay, so the first thing we would have to do is find Q for the reaction, and Q for the reaction will be equal to minus Q for the calorimeter. All right. Now, one thing I can say here without doing any calculation is that because the temperature rises from 19.5 to 21.21, we know that the reaction is exothermic. All right. So that means Q is negative. So let's see here. How do we find Q? All right, let me copy this first and paste it onto the Word document here. Let me lasso all this crap here. And then let me paste this here. Okay, so this is the question. And basically we need to calculate Q. So Q is equal to M times C times delta T. Q is equal to M times C times delta T, all right? So we need to find out what M is and what delta T is. C, we're going to assume, and this is a bit, when it comes to aqueous solutions like these, we can assume that C is basically the same thing as the specific heat of water, 4.18 joules per gram degree Celsius, all right? So question now is, what is M? Well, we have a 50 ml sample of the hydrochloric acid, 50 ml sample of the sodium hydroxide. So the total volume, when you mix them, would be 100.0 mils. All right. Now, how do we get the mass from that? Well, we know that mass is equal to volume divided by, I'm sorry, what am I saying? We know that density is equal to mass over volume. So therefore, the mass is equal to the density times volume. Now, again, we can assume that the density is 1.00 grams per mil, same as water, multiplied by 100.0 mils. So this works out to be 100 grams, all right? So that's the M. So we have the M, we have the C, we have the, well, we can calculate the delta T. So Q would be equal to 100 grams times 4.18 joules per gram degree Celsius times delta T, which would be the final temperature minus the initial temperature, which is 19.5 for both solutions. So we're gonna have 21.21 degrees Celsius minus 19.50 degrees Celsius. And let's see what that gives. So that's 21.21 minus 19.5. So this part gives 1.71 degrees Celsius. And then I'm going to multiply that by 4.18 times 100. And according to my calculation, this works out to be equal to 715 joules. All right. So that's that would be Q of the calorimeter, right? Now, because the reaction, let me erase this here. Because the temperature of the calorimeter increased, we can therefore say that Q of the reaction will be equal to minus Q of the calorimeter, which will be equal to minus 715 joules. So this is the final answer right here, minus 715 joules. All right. So that's the heat that is produced in this reaction given these conditions. All right. Now, the second, any questions about this before I move on? Any question? Any questions? Okay, now the other question that's asked on the same slide, going back to the PowerPoint slide here, is dealing with the same reaction, but this time it says you are to determine the value of delta H based on the equation, right? And you'll notice in this equation here, there's a 1-to-1 mole ratio between the sodium hydroxide and the hydrochloric acid. So basically what you need to find is delta H based on 1 mole of each of these. Now, according to the question, the volume is 50 mils for each of them, and the molarity is 0.250 m. So what that means, therefore, going back to this, I need some space here. So, or yeah, I can scroll down. Okay. So what this means is that we need to find the moles of both hydrochloric acid and sodium hydroxide. And that's easy because the number of moles of HCl, which is the same thing as the number of moles of NaOH, is going to be equal to 50 point, how many sig figs for the 50? 50.0 mils. Convert to liters, so you're going to have 1 liter over 1,000 mils. And then we'll multiply by the molarity, which is 0.250 moles per liter. So this goes with that, that goes with that. And the answer becomes 50 divided by 1,000 times 0.250. Okay, so according to my calculation, this becomes 0.0125 moles. All right. So basically, for this amount of both hydrochloric and sodium hydroxide in terms of moles, the enthalpy change is this. So the question is, what would be the enthalpy change for 1 mole? And the answer is very simple. You take, so delta H for the reaction would be equal to the 715, the minus 715 joules, divided by the 0.0125 moles. So according to my calculation, this results in an answer of minus 57200 joules per mole. Or if you want to express it in kilojoules per mole, it's going to be minus 57.2 kilojoules per mole. And that's how you do that. All right. So that's how we answer that question. Okay, any questions about this? Any questions? Any questions? All right, so let's move along. Oh, actually, I don't think we have time to. All right, I'm going to stop here for today because it's now 1:42, and I don't want to start this topic and then stop in the middle of it. So that's it for today. Oh, by the way, let me see here. Okay, so based on what we have covered so far, you should also be able to do questions 7 and 8. So make sure you attempt those questions. If you have any problems with any of those questions, please, please, please see me or contact me about it, all right? All right, so that's it for today, folks.